Imagine you're trying to solve a puzzle so incredibly complex that finding the perfect answer would take 1,000,000 years. What if you could use a bit of strategic luck to find a really good enough answer in just a few seconds? That's the fascinating core idea behind what we'll explore today: randomized approximation algorithms. We'll learn how clever algorithms can leverage randomness, much like the roll of a die, to quickly find incredibly efficient and valuable solutions to problems that are otherwise impossible to solve optimally. It's all about getting great results, fast, even when perfect isn't an option. Ready to see how probability can be a powerful problem-solving tool? Let's dive in. Okay, so we've introduced randomized approximation algorithms and touched on the core concepts of randomness and value. But how do we actually approach these incredibly complex, often notorious NP-hard problems? This slide outlines the various methods we employ for tackling them. First up, we have branch and bound, often referred to as B&B. This is a general technique used to find optimal solutions across a range of optimization problems. Then, we explore meta-heuristic search methods, like the popular genetic algorithms. We can also employ powerful statistical learning approaches, such as expectation maximization and Gibbs sampling. Another distinct category is fixed parameter algorithms. Finally, and perhaps most relevant to our topic, we have approximation algorithms. These come in several types. Asterisk. There are deterministic algorithms. Asterisk. Then, of course, randomized algorithms, which are highlighted here in red, as they're our main focus. Asterisk. We also use relaxation techniques. Asterisk and polynomial time approximation schemes. This brings us directly to our main topic, randomized algorithms, which we'll explore in much more detail very soon. All right, let's shift our focus now to a fundamental concept, the expected value. To understand it, imagine a random variable, x. This variable can take on various outcomes. For example, it might take a value x sub 1 with probability p sub 1, a value x sub 2 with probability p sub 2, and so on. The expectation of this random variable x, often denoted as ex, is then defined by the formula you see on screen, equals x sub 1 multiplied by p sub 1, plus x sub 2 multiplied by p sub 2, and so forth, all the way up to x sub k times p sub k. In essence, the expected value is calculated by simply multiplying each possible outcome by its respective probability and summing all these products. It's like a long-term average if you were to repeat the experiment many times. Building directly on our understanding of expected value, this slide introduces a fascinating application, randomized approximation algorithms. What's truly exciting is that these randomized algorithms can be incredibly effective, even for solving notoriously difficult nitrogen monophosphide hard problems. When we employ them, our primary interest centers on the INS expected cost of the approximation solution, specifically how it compares with the optimal solution. This crucial relationship is often expressed by the formula you see, C star divided by the expected value of C, where C star, of course, represents the optimal cost. And it is precisely these characteristics, their randomized nature and focus on approximation, that lead to them being specifically called randomized approximation algorithms. Building on our discussion of NP hard problems, this slide introduces a fundamental one, the concept of 3 SAT. So what exactly is 3 SAT? It asks a fundamental question. Given a Boolean expression in conjunctive normal form, or CNF, where each individual clause contains exactly 3 variables, is it possible to find a truth assignment for those variables that satisfies the entire expression? In other words, can we assign true or false to each variable so that every single clause becomes true? Let's look at an example below to make this clearer. Here, we see such a Boolean expression. It's a conjunction of 3 clauses. The first clause is x1 OR not x2 OR not x3. The second clause is x1 OR x2 OR x4. And the third clause is not x1 OR not x3 OR not x4. Notice how each of these 3 clauses indeed contains exactly 3 variables, just as required. So if 3 SAT asks if we can satisfy all clauses, what happens if we can't? That's where max3 SAT comes in. Here, for a given 3CNF instance with times clauses, the problem challenges us to find a truth assignment that satisfies the maximum possible number of those clauses. It's about optimizing, not just a simple yes or no answer for satisfying everything. Now, a really central question we'll tackle is how to design a time-randomized algorithm times to solve this. For example, consider the 3CNF formula you see here. It's made up of 3 clauses: x2 OR not x3 OR not x5, x1 OR x2 OR x4, and not x1 OR not x3 OR not x4. So, continuing our discussion on max3 SAT, let's reiterate its definition. Given an instance of 3CNF with times CN clauses, our objective is to find a truth assignment that satisfies the maximum possible number of these clauses. Now, remembering our central question about designing a randomized algorithm, let's consider the simplest possible type 1 for this problem. This algorithm is incredibly straightforward. It just randomly assigns either true or false to each variable, with a probability of 1/2 for each assignment. As you can see, and as the slide emphasizes, this approach applies absolutely no intelligence whatsoever. It's completely random. But here's the fascinating part, and the key question we need to address. How good is this seemingly unintelligent algorithm? How effective can pure randomness really be? We're going to dive into its performance next. Okay, so we just discussed the simple randomized algorithm for max3 SAT. Now, to truly understand how good it is, as we asked previously, this slide dives into the analysis. Specifically, we're going to tackle a crucial question. What is the probability of a times single clause being unsatisfied by this algorithm? Remember, this algorithm randomly assigns either true or false to each variable, each with a 1/2 probability. Let's look at an example. Below, you see a conjunctive normal form, or CNF, expression. It's made up of 3 clauses, all connected by AND operators. The first clause is x2 OR, not x3 OR, not x5. This is ANDED with x1 OR, x2 OR, x4, which is then ANDED with not x1 OR, not x3 OR, not x4. So, how exactly do we determine the probability that such a clause, or even this entire expression, becomes unsatisfied under our totally randomized assignment? Let's figure it out. Alright, so let's really zoom in on the specific probabilities here. Building on our previous discussion, we're still using that randomized algorithm that assigns a true or false value to each variable with a probability of 1/2, remember? A key question we're addressing is, what is the probability of a clause being satisfied under this random assignment? Now here's an interesting point. While we want to know about satisfaction, it's often simpler to first calculate the probability of a clause being unsatisfied. And under this exact approach, the probability of a single clause being unsatisfied is surprisingly precise. It's 1/8. This calculation assumes the clause has 3 literals, just like the individual clauses shown in the example at the bottom of the slide, such as quote, x2 OR, not x3 OR, not x5. That expression, as you recall, illustrates what we mean by a clause within a conjunctive normal form, showing 3 clauses connected by an AND operation. Each of these individual clauses, as you can see, contains 3 literals combined by OR operations. That specific structure is critical for arriving at that 1/8 probability. So building directly on our previous discussion, we established that the probability of a single clause being unsatisfied under our randomized algorithm is indeed 1/8. This immediately tells us that the probability of asterisk satisfying a single clause using this algorithm is a confident 7/8. Now, with this crucial probability in hand, let's calculate the expected number of clauses satisfied by our algorithm. As the formula displayed on the slide illustrates, the expected value of the total clauses satisfied, which we represent as E of C, is actually the expected value of the sum of individual clauses from 1 to m. Thanks to the powerful principle of linearity of expectation, this simplifies beautifully. It becomes the sum of the expected values of each individual clause, C sub I. And since we know the probability of satisfying each clause C sub I is 7/8, we can conclude that the total expected number of satisfied clauses is simply m multiplied by 7/8. Pretty straightforward, right? Building on our analysis of the expected number of satisfied clauses, let's now consider the optimal solution for this problem. We denote this optimal solution as C star, and it's inherently bounded by m, meaning it can't exceed the total number of clauses. Now, if we compare C star to E of C, you'll see a crucial relationship. Specifically, C star divided by E of C is less than or equal to m divided by m multiplied by 7/8. The m's conveniently cancel out here, simplifying this expression to a neat 8/7. So what does this significant result tell us? It means our algorithm is a randomized 8/7 approximation algorithm. Or, as the slide aptly puts it in simpler terms, it's not so bad. This ratio clearly indicates a reasonably good performance for our algorithm, which is quite a positive outcome. Building on that reasonably good performance we just discussed, let's now summarize the key takeaways regarding our randomized algorithm. As we've seen, we've introduced an 8/7 approximation randomized algorithm, specifically designed for the Max 3 SAT problem. It's really important to remember that 8/7 represents the end expected Nye approximation ratio. In real-world experiments, the actual ratio might fluctuate, potentially being even better or a bit worse than 8/7. So for practical applications, we need to execute this randomized algorithm multiple times. By repeating it and running many iterations, we can then select the very best solution found. This approach helps us get a closer, more refined solution to the problem at hand. So, while we just delved into a specific 8/7 approximation for Max 3 SAT, this slide shifts our focus to the more general NOMS or Max KSAT problem. What exactly is Max KSAT? Essentially, given a KCNF formula with times Dmstus clauses, the problem asks us to find a truth assignment that satisfies the maximum possible number of these clauses. And, tied directly to our previous discussion on randomized algorithms, a crucial question immediately comes to mind. What is the approximation ratio if we were to simply use a random assignment? To give you a clearer picture, take a look below. You'll see an example of a KCNF formula illustrating precisely the type of logical expression we'll be working with. Building on our previous discussion of Max KSAT, let's now broaden our scope to general MaxSat. So what exactly is general MaxSat? Given any satisfiability or SAT instance, the core goal of MaxSat is to find a truth assignment that satisfies many clauses as possible, even if it means not satisfying all of them. Just like we considered for Max KSAT, one straightforward approach to approximating MaxSat is to simply assign true or false to each variable completely at random, with a probability of 1/2 for each. Now let's consider the probability of satisfying a single clause, denoted as C_I. With this random assignment strategy, the probability that a clause C_I is satisfied is at least 1 minus 1 over 2 raised to the power of the number of literals in C_I. Why is this value always greater than or equal to 1/2? Well, it's because a clause can contain as few as just one literal. Moving on, if we let time times be the total number of clauses, we can analyze the approximation ratio of this random assignment. The ratio of the optimal number of satisfied clauses, denoted as C star, to the expected number of satisfied clauses, EC, is less than or equal to asterisk k dimes divided by times k dimes over 2, which, as you can see, simplifies cleanly to just 2. This is quite significant. It means this randomized assignment actually gives us a 2 approximation for the general MaxSat problem, a simple yet powerful result. Next up, we're presented with an intriguing graph problem. Here, we're given n activities and m persons. Each activity has 2 possible slots, either in the morning or in the afternoon. And here's the catch. Each person is interested in exactly 2 activities. Our core task: we need to schedule these activities strategically to maximize the total number of people who can enjoy times both of their preferred activities. The problem we just outlined, dealing with activities, people, and their preferences, can indeed be viewed as a type of graph problem, And that leads us directly to what we'll explore on asterisk this slide, the concept of max cut. So what exactly is max cut? At its heart, it's a specific formulation of clustering problems. The main goal is to take a given set of nodes, imagine points connected together, and consider the distances or relationships between them. Then your task is to partition these nodes into two distinct clusters, or separate groups. The graph you see right here on the slide visually represents precisely this kind of setup, a collection of nodes and their interconnections that we would aim to divide into those two separate groups. To illustrate the max cut concept we just introduced, let's now look at the max cut problem in more detail. Here, the nodes we talked about, or the activities we're analyzing, are represented as node vertices, and each edge asterisk connecting these vertices represents a specific connection, in this case, one person. Take a look at the right side of the slide. You'll see a visual representation of such a graph. Notice the orange circles serving as our times dunderized vertices, and the black lines acting as the times dunderized. Now, see that gray curved line? That's what we call a asterisk cut, asterisk through the graph. It literally divides our set of vertices into two distinct groups, or sets. And here's the core challenge. The entire goal of the max cut problem is to intelligently find asterisk, the best possible cut, NIMES one that maximizes the number of edges crossing this dividing line asterisk. Want to see this in action? For a practical, hands-on demonstration, I highly recommend exploring the application available at the Berkeley link provided directly on the slide. It's a great way to visualize these concepts. Building on our foundational understanding of graph structures, let's delve deeper into how they can be represented and interpreted. This slide showcases two illustrations of the very same underlying network structure, but with different sets of nodes and edges highlighted. On the left, you'll observe a graph comprising 7 circular nodes. Notice how 3 of these nodes are distinctly encircled in red, drawing immediate attention. Additionally, 5 of the connections or edges are depicted as thick black lines, perhaps indicating a specific path or active connections, while the remaining 4 edges appear as thin and gray. Now shifting our focus to the right side, we still have the exact same times graph structure. However, a completely different set of 3 nodes are now highlighted with red circles. Consequently, a new set of 5 edges are depicted as thick black lines, representing a distinct emphasized path or selection within this identical network. This side-by-side comparison truly highlights how various components or relationships within a graph can be visually distinguished, even within the same underlying structure. Building on our understanding of how graphs are structured and how different components can be visually distinguished, let's now explore a fascinating challenge known as times the MAXCUT problem, asterisk. At its core, our objective here is to take an undirected graph with n nodes and find a way to partition its nodes into 2 distinct sets. Let's call them set A and set B. The goal? To maximize the total number of edges that connect a node in set A to a node in set B. These, of course, are precisely the edges that cross the cut. To visualize this, take a look at the example graph on the right. You can see it features 6 nodes and several connecting edges. Notice the prominent red curved line representing one such cut through the graph, effectively separating the nodes into 2 distinct groups. The edges that are intersected by this red line are the ones contributing to the size of this specific cut. And remember, the MAXCUT problem aims to maximize these crucial crossing edges. So, how might we go about finding such a maximum cut? One surprisingly simple yet effective approach involves a randomized algorithm. For every single node in the graph, we randomly assign it to set A with a probability of 1/2. Picking up right from our last point, this slide will delve into the analysis of that very randomized algorithm we just discussed. Specifically, we're focusing on the process where, for each node V in a graph G, we randomly assign it to set A with a probability of 1/2. The crucial question we need to answer here is, how effective is this algorithm? How good is it, really? To help us analyze this, let's define M as the total number of edges present in our graph. This immediately tells us that the size of asterisk any possible cut, even the absolute maximum cut, which we'll denote as C star, can be at most m. That's our upper bound, right? So then we naturally ask, what about the expected time approximate solution? How do we quantify that? We represent the expected value of the cut, E, as the sum over every single edge E in graph G of the probability that edge E is actually included in the cut. This formula is key to understanding the algorithm's typical performance. Let's now delve into how this expected approximate solution is derived, which will ultimately lead us to the concept of a two approximation. First, let's clearly define what constitutes an edge in a cut. An edge is not considered a cut if both its ending nodes are placed into the same partition, either both in set A or both in set B. Conversely, an edge knows a cut if its two end nodes are in different partitions, meaning one end node is in partition A and the other is in partition B. Building on that, we then look at the expected value of the cut, denoted as E. As previously discussed, this is calculated as the sum over every edge in graph G of the probability that edge E is included in the cut. What's truly interesting is that this expected value is shown to be equal to m divided by 2, where m represents the total number of edges in the graph. This means that, on average, half of all edges are expected to be part of our cut. Now for the truly powerful insight. When we consider the ratio of C times, which represents the optimal cut, to our expected cut EC, we find that C times over EC equals 2. What does this tell us? This critical result indicates that the optimal solution is, at most, twice the expected value of the solution found by this approximation. And that, ladies and gentlemen, directly leads us to the conclusion. This elegant approach constitutes a two-approximation algorithm for the max cut problem. So, to summarize our findings and truly understand this approach, we've demonstrated a two-approximation algorithm. Critically, it operates with an asterisk expected approximation ratio. However, it's really important to note that while the expected ratio is 2, the actual approximation ratio you observe in real experiments might be better, or indeed worse than 2. Therefore, in practice for a randomized algorithm like this, you'll want to repeat it many times. From those multiple trials, you can then confidently pick the best solution found. Building on our discussion of finding optimal solutions, let's now delve into a fascinating problem, the weighted max cut. You see, in many real-world scenarios, graphs aren't just collections of nodes and edges, they're weighted. This means each connection, or edge, comes with a specific numerical value, its weight. Our objective with weighted MAXCUT is quite clear. We want to intelligently partition the graph's nodes into two distinct sets. Why? So that the sum of the weights of all edges connecting nodes between these two sets, what we call the cut, is as large as possible. Take a look at the example on the right. It beautifully illustrates this concept. Notice how each line connecting the dark gray nodes has a number right next to it? That's its weight, showcasing how these values factor into our problem. So the big question we're really grappling with here is, how do we effectively tackle and solve this challenging problem? Continuing our deep dive into weighted MAXCUT, let's establish some fundamental properties that will help us understand its solution space. On the left, we first define W as the total sum of all individual edge weights in a given graph. This value represents the absolute maximum possible weight if all edges were part of the cut, which isn't always feasible. For any optimal cut, denoted as C star, its value will naturally always be less than or equal to this total sum W. Interestingly, if we were to consider a random cut, its expected value E cos B is neatly shown to be half the sum of these individual edge weights, simplifying to a very intuitive 1/2 W. This gives us a baseline expectation. To help visualize these concepts, on the right, we have a clear example of a weighted graph, precisely the kind of structure these definitions apply to. This specific graph features 7 nodes and multiple edges connecting them, each assigned a numerical weight. You can see examples of these weights: 1, 2, 3, 4, 5, 7, and 9. This visual representation is crucial. It helps us concretely understand how W is calculated, and how the MAXCUT principles we're discussing would be applied in a real scenario. Building on our discussion of weighted MAXCUT, which effectively focuses on dividing a graph into two partitions, this slide introduces a powerful generalization, the concept of asterisk, max, cut. In max cut, instead of just two, the vertices of a graph are partitioned into, quote, distinct groups. The cuts are then precisely defined as the edges that connect vertices belonging to asterisk different groups, emphasizing the connections between these partitions. The accompanying graph visually illustrates this concept perfectly, providing a clear example of a three-cut. Here we observe 8 nodes meticulously partitioned into 3 distinct groups, each represented by a different color. We have 2 red nodes, 2 brown nodes, and 4 blue nodes. Notice how the gray edges are crucial. They connect nodes from different colored groups, vividly representing the actual cuts between these partitions. And just to highlight the difference, there's also 1 black edge connecting 2 blue nodes, which is an example of an edge times within times one of the groups, not a cut. Ultimately, the core objective of max k-cut is to find a partitioning that maximizes the total number, or, for weighted graphs, the total weight of these vital intergroup edges, those crucial connections between your k distinct partitions. Now that we've introduced the concept of max k-cut and seen an example, this slide dives deeper into the max k-cut problem itself. Specifically, it poses a critical question. How do we design a randomized approximation algorithm to solve it? To help illustrate this challenge, take a look at the graph presented on this slide. Here, you'll see several nodes distinguished by 4 different colors: orange, brown, light blue, and dark blue. These colored nodes, as we discussed, represent distinct partitions or sets within the graph, and the lines connecting them are, of course, the edges. Ultimately, as visually suggested by these different colored groups, the max k-cut problem is all about finding the optimal way to partition the graph's nodes into k-sets. In this specific instance, 4 sets, corresponding to these 4 colors, such that the total number of edges running between these different sets is maximized. That's our goal. So how do we design that randomized approximation algorithm for max k-cut? This slide lays out a straightforward 2-step approach. First, and this is quite intuitive, we randomly assign each vertex into one of the k groups. Just look at the graph below. It beautifully illustrates this idea. You'll see 7 vertices, or nodes, that have been randomly assigned to 3 distinct groups, clearly marked by the colors red, gray, and blue. Notice how edges connect these vertices, not just within their own groups, but also between different colored groups. This then leads us to the second crucial question on this slide. How good is this algorithm, really? So, how good is this algorithm exactly? To understand its performance, let's first go through some key definitions and probabilities. First, let's define M as the total number of edges in our graph. It's important to note that the size of asterisk any stock tool, including the maximum possible cut, which we denote as C star, will always be less than or equal to M. This makes sense, as you can't have more cut edges than there are total edges, right? Now, what exactly makes an edge a cut in this context? Simply put, an edge is considered a cut if its 2 end nodes are not assigned to the same group. Let's dive into the probabilities. If we have k groups, the probability of any 2 specific nodes ending up in the same asterisk group is simply 1 divided by k. So, what's the probability of an edge actually being a cut, meaning its 2 nodes are in different groups? Well, that's 1 minus the probability of them being in the same group. This nicely simplifies to 1 minus 1 over k, or more concisely, k minus 1, all divided by k. Finally, we come to the expected value of C, which represents the total times number of cut edges. This value is simply the sum of the probabilities that each individual edge E is a cut. Since we have M total edges and each one has a probability of k minus 1 over k of being a cut, the expected number of cut edges is straightforward. It's M multiplied by k minus 1, all divided by k. This gives us a powerful metric for the goodness of our random assignment. Now that we've defined the components and derived the expected value of a cut, let's see how this ties into the max k-cut problem itself. and a crucial result using a randomized approach. As you can see, the title clearly states, max k-cut. The main takeaway here, prominently highlighted, is that this randomized approach provides A times k over k minus 1 asterisk approximation for the max k-cut problem. What does that mean? It means the algorithm finds a solution that's guaranteed to be within a factor of k divided by k minus 1 of the absolute optimal solution. Let's break down the supporting formulas that lead us to this powerful result. First, recall that C star is less than or equal to m. Just to reiterate, C star represents the optimal value of the max k-cut, and m, as we know, is the total number of edges in the graph. This inequality simply establishes an upper bound for that optimal cut value. Next, we have the expected value of C, denoted as EC. As we just arrived, this equals the sum of probabilities that an edge E is in the cut, and indeed, this sum is equal to m times k minus 1, all divided by k. This crucial formula gives us the expected size of the cut obtained by our randomized algorithm. Finally, by combining these two key values, C star and EC, we arrive at the approximation ratio itself. C star divided by EC is less than or equal to k divided by k minus 1. This inequality formally captures that the ratio of the optimal cut to the expected cut found by our randomized algorithm is bounded by k over k minus 1. This elegantly confirms the approximation guarantee for the max cut problem. Having explored the max k-cut problem and its approximation guarantee using a randomized approach, let's now extend our focus to a more complex, yet common, scenario: the weighted max k-cut problem. Here, our core objective is to take a given weighted graph and find a k-cut that achieves the absolute maximum total weight. But this immediately raises a crucial question, doesn't it? How effective is a randomized algorithm, one that simply assigns each vertex into any of the k-groups, when weights are involved? To help visualize this challenge, you'll find an example graph displayed on the right. It clearly illustrates the type of structure with its nodes and connected edges that we analyze in this intriguing problem. Building on our introduction to the weighted max k-cut problem, let's now explore its key mathematical relationships. First, let's consider C star, which represents the optimal weighted k-cut. We can see it's bounded by an important inequality. C star is less than or equal to the sum of all individual edge weights, W1 plus W2, and so on. This gives us a clear upper bound for the maximum possible cut value we could achieve. Next, we define the expected value of the cut, often denoted as E of C. How is this calculated? It's the sum of each edge weight, Wi, multiplied by the probability that that specific edge E is included in the cut. Interestingly, this expression simplifies quite nicely to K1 divided by K, all multiplied by the total sum of asterisk all edge weights. Finally, we arrive at a truly crucial inequality. It shows the ratio of the optimal cut, C star, to the expected cut, E of C, is less than or equal to K divided by K1. This inequality is vital because it highlights a significant approximation ratio for the weighted max k-cut problem, clearly demonstrating the powerful relationship between our optimal and expected cut values. So having explored those mathematical relationships and the concept of an expected cut, this slide brings us to some crucial concluding remarks. The main takeaway here is really important: pure randomness. For instance, simple random assignment often falls short of approximating the optimal solution in practical scenarios. While it might offer guarantees of solution quality analytically, this frequently doesn't translate effectively to real-world applications. Therefore, to truly significantly improve the actual solution obtained, some form of intelligence is almost always required. So what happens when we do rely on randomness, even without explicit intelligence? Let's examine the classic max cut problem. Here, one common approach involves simply and randomly assigning each vertex to one of two sets. Let's call them set A and set B, with a probability of 1/2 for each. A key and rather remarkable result of this purely randomized approach is that the expected size of the cut you obtain will be at least half the total number of edges in the graph. This expected value also provides a crucial bound related to the optimal solution for the max cut problem. To put this in terms of approximation, the slide illustrates this relationship as C star, the optimal cut, divided by E, the expected cut, equals 2. What this truly signifies is that the expected cut size found using this simple randomized method is guaranteed to be at least half of the optimal max cut. This is a powerful performance guarantee for such a straightforward randomized algorithm, showing its surprising effectiveness. And visually, you can see a graph on the slide. That's the fundamental structure upon which the max cut problem and many other network optimization problems are defined. So building on our discussion of the max cut problem and the randomized approach, we highlighted that the Simon's expected times cut size is at least half the total number of edges. That sounds great, right? However, it's vital to remember that an expected value doesn't mean it's asterisk guaranteed in every single run or iteration of the algorithm. This means the specific solution we discover can actually vary quite a bit from one attempt to the next. So what's the actual likelihood of getting a, quote, in good enough cut? Well, specifically, the probability, P, of obtaining a cut with a size of at least half is given by this inequality. P, is greater than or equal to 1 divided by the quantity m over 2 plus 1 foot. Now, let's think about a practical scenario. What if you were required to get a cut with a size of at least half the total number of edges? That's about n in every single iteration. Given this variability we've just discussed, what strategies or modifications could you possibly employ to meet this much stricter requirement? So, picking up directly from that challenge we just posed, how we guarantee a cut size of at least (2) in every single iteration. This is precisely what we'll delve into on this slide, aptly titled Randomization to Determinism. One immediate thought to address this stricter requirement would be to repeatedly run our existing randomized algorithm. Specifically, we could consider repeating it m/2 plus 1 times. While this approach dramatically increases the likelihood of eventually obtaining a cut of at least (2), the expected running time for doing so would be (OM squared). As you can imagine, running the algorithm this many times can become quite time-consuming and computationally expensive. This leads us to a crucial question, doesn't it? Is there an asterisk alternative way to guarantee a solution of at least (2) in each and every iteration without incurring the significant overhead of repeated randomization? This fundamental question marks a key transition in our discussion, moving our focus from purely randomized approaches to exploring more deterministic methods for achieving that guaranteed cut size. And this is where de-randomization comes into play. So the core question we're really addressing here is, can we guarantee a solution of at least (2) in every iteration without simply relying on probability? This line of inquiry leads us to two critical points. First, we want to completely avoid relying purely on luck to achieve a feasible solution. And second, the fundamental goal of de-randomization is to transform a randomized algorithm into one that essentially behaves like a deterministic algorithm. This is particularly important for its performance guarantees, like achieving a specific worst-case ratio. Building on our previous discussion about its goals, let's now truly define de-randomization. Essentially, de-randomization refers to methods for eliminating uncertainty in randomized algorithms. This often involves revising the original randomized algorithm and leveraging probabilistic analysis to achieve those strong performance guarantees we discussed. Now, to make this concept more concrete, let's walk through an example of a greedy algorithm in action. It all begins by initializing two sets, set A, which contains a starting node, denoted as V1, and an empty set B. Next, we randomly pick an unpartitioned node. We then observe its neighbors, and the crucial step is to place that node into the set that currently has fewer neighbors. This entire process is then repeated, iteratively, until every single node has been partitioned. Building on the example we just introduced, let's dive deeper into how this specific greedy algorithm for graph partitioning actually works. As we discussed, the process kicks off by initializing two sets. Set A, which begins with a single starting node, V1, and set B, which is initially empty. Now, for the core greedy step, we continue by randomly picking an unpartitioned node from the graph. The clever part is, we then carefully observe its connections, its neighbors, to nodes already residing in set A and set B. Based on these observations, we make a critical choice. We place the chosen node into the set where it has fewer existing neighbors. This isn't just arbitrary. This strategy aims to take care of the weaker side, potentially minimizing connections to the more densely populated partition, or simply striving to balance the sets. It's really important to note, while the potentially selection of the node itself is random, the placement decision once selected is entirely deterministic. Once we know those neighbor counts, there's no further randomness in that specific choice. To truly visualize this process, let's look at the diagrams at the bottom of the slide. On the left, you'll see a white node. If we assume blue nodes are in set A and gray nodes are in set B, this white node has one neighbor in A and two in B. Following our greedy rule of placing it in the set, with thunderstorm Tanya read neighbors, where would it go? Naturally, it would be placed in set A. The diagram on the right then shows the outcome. The white node has now transformed into a blue node, clearly indicating its addition to set A, perfectly consistent with our greedy strategy. Alright, so how does this greedy strategy play out in practice? Let's walk through a concrete example right here on this slide. On the left, you'll see two indicators, an empty circle outlined in blue and another in orange. These will help us track the node states throughout the process. To the right, we have our starting graph, consisting of 6 interconnected red nodes. Take a closer look at the bottommost node in this graph. It's currently highlighted with a blue outline. This matches our blue indicator on the left, showing us that this TARS is the selected or active node we're focusing on for this step. Continuing with our examples, here we're looking at another illustration, specifically a more detailed graph or network structure. Notice the 7 interconnected nodes, clearly represented by red circles, with their connections visually depicted by gray lines. What's immediately apparent are the 3 specific nodes that stand out, one at the very top, outlined in orange, and then 2 others with a blue outline, one positioned on the right side of the graph and another towards the bottom. This visual truly helps us grasp how various elements can be interconnected and relate to each other within a broader network. Continuing our exploration of network structures, here's another example of a graph. This one features 6 interconnected nodes, beautifully represented by the reddish-brown circles. And just like before, those gray lines are the connections, or edges, that link them together. Now, for this particular illustration, I want you to focus on 2 specific nodes, the one right at the very top, highlighted with a bright red circle, and the node down at the bottom, clearly marked with a blue circle. Building on our last example, let's dive into another network diagram, or graph. Just like before, we have a collection of 6 reddish-brown nodes, interconnected by various gray lines that represent the graph's edges. What's interesting here is that certain nodes are highlighted with colored outlines. Specifically, 2 nodes are encircled in blue, and 2 others have an orange or reddish outline, drawing our attention to specific elements within this example graph. Picking up from our last slide's example, this one provides an even clearer view of a graph or network structure. Here we see 6 circular, brown-colored nodes, all interconnected by gray lines that serve as the graph's edges. And notice this, 4 of these nodes are distinctly highlighted with an orange outline, while the remaining 2 are clearly outlined in blue. These highlights help us pinpoint specific elements or properties within this example network, drawing our attention right where it needs to be. Building on our previous example, here's another network graph. You'll notice this one is composed of 7 reddish-brown nodes, all interconnected by dark gray lines. And similar to the last slide, 5 of these nodes are highlighted with an orange outline, while the remaining 2 are distinctly outlined in blue. Okay, now that we've looked at an example graph, let's dive into the analysis part of our discussion. To begin, let's define "m" as the total number of edges in our graph. As the algorithm executes, we'll consider these edges in 3 distinct categories. First, "CAB" represents the number of edges that are currently included in the cut. Next, DAB denotes the number of edges that are not asterisk in the cut. And finally, XAB signifies the number of edges where at most one of their connected nodes has been assigned. It's crucial to understand that initially all edges would fall into this XAB category. So the total number of edges M can always be expressed as the sum of these three categories. M equals CAB plus DAB plus XAB. Here's an important property that holds true in every iteration of the algorithm. CAB is always greater than or equal to DAB. I encourage you to ponder why this property consistently holds. The image at the bottom of the slide visually depicts a network structure with nodes and edges, illustrating the very kind of graph we're analyzing here. Building on our definitions from the previous slide, let's now delve deeper into how our node assignment algorithm works and, crucially, why that interesting property we just discussed consistently holds. As we defined earlier, our total number of edges, M, is always the sum of these three crucial components, CA, B, D, A, B, and XA, B. Remember, these terms quantify distinct types of connections within our evolving graph structure. So what happens in each iteration? A new unassigned node comes in and is strategically assigned to either set A or set B. This assignment directly impacts and dynamically updates our CA, B, or DA, B, counts, reflecting the ever-changing connectivity of our graph. And here's the crucial part, the why behind that property we touched on. A fundamental rule of our algorithm is to always place the new node into the set where it has fewer existing neighbors. This incredibly specific placement strategy is precisely what ensures that CA, B, those connections to the other set, is always greater than or equal to DA, B, which represents connections to the chosen set. So, as a direct consequence of this strategic assignment, the inequality CA, B, greater than or equal to DA, B, becomes a truly fundamental property that consistently holds true throughout every single step of our algorithm. It's a cornerstone of its effectiveness. To help visualize these concepts, let's now turn our attention to the diagrams at the bottom of the slide. The figure on the left perfectly illustrates a new, unassigned node, depicted as that white circle. Notice how all of its potential connections to existing nodes, both the blue ones and the gray ones, are initially labeled with X. This helps us visualize precisely what X of A, B quantifies. The initial, unassigned connectivity of a node before interesting to ride, it's placed into either set A or set B. Moving to the figure on the right, this diagram beautifully clarifies the distinct nature of our C and D connections. A D connection, as you can see, signifies an edge between nodes within the same assigned group. Think of it as a connection between two blue nodes or two gray nodes. Conversely, a connection clearly represents an edge between nodes belonging to asterisk different groups, like an edge going from a blue node to a gray node. Together, these diagrams truly help us visualize exactly what C and D are quantifying in this crucial partitioning process. Building on our previous discussion, let's now formally define M as the total number of edges in our graph. As the algorithm executes, we categorize these edges into three specific types. First, CA, B represents the number of edges currently names in the cut, meaning they connect nodes in different sets. Next, DA, B refers to edges that are asterisk not in the cut, connecting nodes within the same set. And finally, XA, B denotes edges where at most one of their connected nodes has been assigned yet. Crucially, the total number of edges, M, is always the sum of these three categories. M equals CA, B plus DA, B plus xa comma b. Now, recall a key property we discussed earlier. Ca comma b is always greater than or equal to da comma b throughout the algorithm's execution. What's more, when the algorithm finally terminates, all nodes have been assigned, meaning xa comma b becomes 0. This leads us to a truly significant conclusion. Upon termination, a comma b will be greater than or equal to m divided by 2. This means that at least half of the total edges will always be found in the cut when our partitioning is complete. The accompanying diagram on the slide provides a visual representation of a generic graph, helping us visualize these very components, its nodes and edges, as we've discussed them in this analysis. Building on our previous analysis, where we concluded that our approximation solution C of A comma B is always greater than or equal to m divided by 2 upon termination, this slide now shifts our focus to understanding what a two-approximation algorithm truly means in this context. So, what exactly defines a two-approximation algorithm? Why asterisk? Essentially, we're comparing our approximate solution to an optimal one. The optimal solution, C star, will always be less than or equal to m, the total number of edges. Asterisks. And as we just established, our approximation solution, Ca comma b, is guaranteed to be greater than or equal to m divided by 2. Asterisks. When we put these together, we get a crucial ratio. C star, our optimal solution, divided by Ca comma b, our approximation, will always be less than or equal to 2. This is powerful, as it tells us that our approximation solution is, at worst, only twice as bad as the absolute best possible solution. It's important to note that this two-approximation represents the worst-case scenario for our algorithm. This naturally leads to a critical question for us to consider in practice. How can we potentially improve this during implementation? To give you a visual anchor, take a look at the bottom of the slide. You'll see a simple graph representation, a set of interconnected nodes and edges, with some nodes highlighted by blue circles. This visual serves to illustrate the very structures we're analyzing when applying this algorithm. So if the two-approximation represents a worst-case scenario, how do we actually approach problems like this? Well, on this slide, we're diving into a specific and widely used technique, the greedy algorithm, applied to the weighted max k-cut problem. Our core question here is pivotal. What exactly is the approximation ratio, denoted as C time over C, for the weighted max k-cut problem when we employ this greedy algorithm? To clarify the greedy approach, it's quite straightforward. It involves assigning each vertex to the group that produces the largest weight of cut edges. It's about making the locally optimal choice at each step. In this context, C represents the optimal solution, the absolute best possible outcome. And C, of course, is the solution found by our greedy algorithm. You'll then see how we justify the bounds for these two crucial values. To make this more concrete, on the right side of the slide, you'll see a practical example of a weighted graph. This visually illustrates the very type of problem we're discussing, complete with various nodes and edges, each assigned different weights. It helps bring the abstract concepts to life. All right, as we wrap up our look at the greedy algorithm, let's dive into some key concluding remarks. One crucial point to highlight is that a time-single run of a greedy algorithm can often waste computing power. So how do we address this practical limitation? Well, in practice, it's common to randomly select initial seeds and then repeat the greedy algorithm multiple times. You'll see this approach in well-known methods like expectation maximization, or EM for instance.